All right, this is for Cindy and others. Just wanted to go over this idea they asked. If you were to drop a penny from the Empire State Building, would it be damaging to people below? So let me do my best. Empire State Building. I think it's something like this. It has sort of like a little spire on the top. And I take a little penny and I drop it down, and it drops a certain distance. Let's see, now, really what we're looking at here is we want to know, or what's important rather, is the energy that the penny has. All right, and then let's compare it to the energy of a bullet. All right, now kinetic energy, which you've probably learned in your physics or physical science class, is related to the mass and the square of the velocity. It's 1/2 mv squared. And now let's just calculate what is the kinetic energy of a bullet. So I can take, let's say that my mass of the bullet, let's say that it's a pretty big bullet, about 30 grams. So the mass of my bullet is 30 grams, that's 0.03 kilograms. And it has a velocity of, say, 300 meters per second. Pretty typical for a bullet. So it's a big bullet traveling at a pretty typical speed. So it should give us sort of an upper limit on the energy, that's squared. And that tells us that the energy is 1,350 joules. Now I know that a bullet, if it hits me, is going to hurt me, okay? And it has an energy of roughly 1,350 joules, around that order of magnitude, 1,000, 2,000, 3,000 joules. All right, so I want to know then, what is the kinetic energy of this penny? And does it come anywhere close to the kinetic energy of a bullet? So let's just take a first pass. All right, I want to know the mass of the penny. And I looked this up on Google. You can just Google mass of a penny. And let's see, the mass of a penny is 2.5 grams. That's 0.0025 kilograms. All right, 0.0025 kilograms. And then now I want to know also what is the velocity of a penny. All right, now it falls a pretty high distance. It falls actually the height of the Empire State Building, which I looked up, is 381 meters. So this height is 381 meters. And I want to know, if my velocity is 0 at the top, what is the velocity of the penny at the bottom? And then that's what I'm going to plug in here in order to find my kinetic energy. I can do this by looking at the conservation of energy. I know that the kinetic energy at the top is 0. So up here at the top, this penny has 0 kinetic energy, and its potential energy is equal to mg times h. And down at the bottom, the potential energy is equal to 0, and the kinetic energy is that 1/2 mv squared. Now the conservation of energy says that the energy up here is equal to the energy down there. That all throughout its trajectory, that penny keeps the same amount of energy. Right? So since that's true, I can say that the potential energy at the top equals the kinetic energy at the bottom. All right, so I get mgh equals 1/2 mv squared. Potential energy at the top equals kinetic energy at the bottom. And then I'm going to solve for v, and then that's going to be the velocity or the speed of the penny at the bottom. Let me cancel out my masses. And I'll solve this for v at square root of 2gh. That's the square root of 2 times 9.8. That's the acceleration due to gravity. That's what's causing it to accelerate, times the height, which is 381 meters. All right, so it's coming to a velocity of 86 meters per second. All right, so that's sort of my upper limit. That's the maximum speed that this thing can go, at 86 meters per second. We'll come back to that in just a minute. So my velocity up here is 86 meters per second. So now I can find the kinetic energy. I could have done this another way, but I'm just going to do it this way. 1/2 mv squared, all right, which is going to be half times 0.0025. That's my mass in kilograms, times 86 meters per second squared. And then that gives me my kinetic energy. And when I find it, I'm going to compare it to this number. Now let's see, that gives me a kinetic energy 9 joules. 9 joules. All right. Now, how does 9 joules compare to 1,350 joules? Now, it's a lot smaller, right? And in fact, you might say, well, you know what? You really chose a pretty big bullet, because a 30-gram bullet, that's a pretty big bullet. But even if we were off by a factor of 10 up here for the mass, like say instead of 0.03 kilograms, we decided instead to have 0.003 kilograms, then it would just give us 135 joules. Now you see the big behemoth here is the velocity. And 300 meters per second, that's pretty typical for a bullet. 300 meters per second. I'm not going to give on that. I'll give on the mass of the bullet, because those can have a wide range. But we're looking at hundreds or thousands of joules in the kinetic energy of a bullet. So hundreds or thousands of joules as to what's going to harm us in this scenario. And the kinetic energy of our penny is minuscule compared to that, just a small fraction, a tenth, a 1%, a hundredth, or even smaller. Okay, so just sort of a first broad pass, we would say, well, this penny's probably not really going to hurt you, because it's not really going fast enough to hurt you. But we can further solidify that, because we haven't even really considered the terminal velocity. Now, if I have a falling body, let's say this is my penny. Here is this is the guy, Abraham Lincoln, on top of it. He's falling. Some eyes and a mouth. He's falling, and there are two forces at work. There's the weight of the penny, and then there's the force due to air resistance. I'll call that Fa. Now, at some point, the force due to air resistance is going to equal the weight. Now, when that occurs, when the force due to air resistance equals the weight, then the penny will no longer accelerate. The acceleration will equal to 0 when those two forces are equal. So we need to figure out what is this velocity when the air resistance, the force due to the air resistance, is equal to the weight. And this is called the terminal velocity. I can calculate the terminal velocity. I'm not going to get into how we do this, but I can calculate the terminal velocity. I'll call it Vt is the square root of 2mg divided by d times rho times a. D is the drag coefficient. It's based on the shape of the object, the shape, and the type of material. It's the drag coefficient. You can find a nice piece on Wikipedia about terminal velocity and drag and all that, probably more than you really want to know. Rho is the density of air. It's the density of the fluid through which it's traveling. In this case, that's going to be air. And then, what else do I have? Oh, A is the area of our object. And we're going to give a worst case scenario that this penny is falling flat side down. That's going to give us the most drag. All right. A is the area. What else do I have? Oh, M is the mass. We've already given that. And then G, of course, is the acceleration due to gravity. All right. That gives us the weight. The M times G gives us the weight. Now, the drag coefficient. This is determined experimentally, and that's really the key variable here, because we don't really know what the drag coefficient is very well without doing it experimentally, because it's dependent upon the shape of the object, but also what the object does when it's falling through the atmosphere. So if I have this penny, if it falls flat without spinning, it's going to have one drag coefficient. But if it falls and it spins in the air, then it's going to have another drag coefficient. Now, I looked it up actually on Wikipedia, and I learned that the drag coefficient for this particular scenario, or actually for most scenarios, is going to range somewhere between 0.5 and 2. All right, somewhere between 0.5 and 2. The density of air is 1.28. That's in kilograms per cubic meter. It's the density of air. And the area of a penny, you can look this up, but I found the diameter was 0.19 centimeters. And so that gives me the area is 2.83 times 10 to the minus 4, square meters. The mass I've already given, and there's g. I use the worst case scenario. If I use d equals 2, when d equals 2, that gives me a terminal velocity, putting in all those values, of 8.2 meters per second. Or excuse me, that's the best case scenario. When d equals 0.5, that gives me a terminal velocity. So I have the least amount of drag here. Gives me a terminal velocity of 16 meters per second. All right, and so if I use those, let's see, I don't think, oh yeah, here we go. At 8 meters per second, my kinetic energy, remember 1/2 mv squared, my kinetic energy is 0.008 joules. At 16 meters per second, my kinetic energy is 0.32 joules. So we're talking very, very small fractions of the original energy that we were comparing it to. Remember, that was the energy of the bullet, and that's 1,350 joules. So in a more realistic scenario, it becomes even less likely that this penny would cause any damage at all. But you know what? You can do a pretty easy experiment, because we know sort of what the terminal velocity is, or at least we have an upper limit on what the terminal velocity is. That's 16 meters per second. So we ask, well, what height do we need to drop this to get to v equals 16 meters per second? And we can go back to our conservation of energy. That is, I'm going to drop a penny from a certain height. I want to drop it such a height so that at the bottom the velocity is 16 meters per second. And so what is this h? So I just say mgh equals 1/2 mv squared. That's potential energy at the top is equal to the kinetic energy at the bottom. And then I solve for h using v equals 16 meters per second. And I get h equals 13 meters. You know, that's about 40 feet or so. So I think the best thing that you can do is you can go to the top of the stairwell. I think you'll have some external stairwells at E.D. White, and drop a penny onto somebody's head. And if it kills them, then obviously you have the answer to your question. But if it doesn't really bother them, then you've just proved it. All right, you've shown that a penny that reaches that speed of 16 meters per second, which is the speed that it's going to reach drop from the Empire State Building, won't do any damage. Okay, I think that's probably the best thing you do. So just go up there, drop a penny onto somebody's head. You can try some heavier things like batteries or you know, barbells or whatever, but and see, do a whole range of experiments, and well, maybe that's not such a good idea. So I guess the quick answer is that no, that in my opinion, it won't affect your brain too much.